These are the problems we just ran out of time, you know. So what we're looking for in order for us to call things independent, dependent, or inconsistent, we've talked about how consistent is what we like in math. We like to say, hey, here's the answer. We want to be able to give them something when they say find the solution. So if we actually find an answer, let's say we find the point ordered pair 4, 2. That's consistent with what we like at math. We even like to be able to say infinitely many solutions. And that happens when you realize that it's really the exact same line. You know, the line is going right over the top of another one. In the colors that we had yesterday up here, the red and the blue made purple because they were right over the top of each other. So that's consistent. Inconsistent is when we have to say there isn't any solution. Now that only happens when the lines are parallel. So we think about how we would know numerically with just equations, we wouldn't have to graph these. Well, if we see they have the exact same slope, but they don't have the same b value, those are parallel, so we're going to write inconsistent for that. Now that we know which ones are consistent and which ones are inconsistent, then we say, well, what about this independent and dependent thing? Well, if you just get one answer, this is an independent solution. Independent means to be by yourself. If it's one solution, that's what you have. But the infinitely many, that's definitely more than one. You know, it's infinitely more than one. So this one is dependent because your solutions are dependent on the fact that they have gone right over the top of all of the solutions of the exact same line. So what we're looking for here is this. When we solve these for y, are they exactly the same? If they're exactly the same, we're going to write infinitely many solutions and dependent. Are they parallel? Are the slopes the same but the b values are not? Then we're going to write no solutions and that it's inconsistent. If none of that happens, you're going to get one answer. And those are the only three choices you have. And if you get one answer, that's consistent with what we like, and it's independent because there's only one. So this says, without graphing, and granted in the homework they're going to say with some of them, go ahead and graph it. But it makes it a little easier when you know what's going to happen beforehand. We want to solve for y. So our top equation here is negative 3x plus y equals 4. Not too bad solving that for y. We're going to go ahead and add 3x to both sides. And then the bottom equation down there is x minus 3y, x minus 1/3 y equals 1. And I was just thinking, if you don't like working with fractions all the way through, you certainly could go ahead and multiply everything here by 3. So maybe that's what we decide to do. You know, we don't want to work with fractions. Multiply it all by 3. But don't forget about the right side over there. And then we say, okay, now this is easier. I'm going to subtract 3x from both sides. Negative y equals negative 3x plus 3. And I realize not done yet because I need to divide by a negative 1. Now I have these as y equals. Now's the time to compare those and see what's going on. So I notice they've got the same slope. They don't have the same b value in the back. They don't. So if they have the same slope, these lines are going to be parallel. And that means we're going to have to write no solutions because they're not going to hit each other. And that's the thing we don't like in math, having to write no solutions. So that is inconsistent with what we like. Inconsistent. So it's all about solving it for y and then taking a peek at it to see, is the slope the same? Is the slope and your y-intercept the same? And then what does that tell you as far as the vocabulary goes? So for B, we have 2x plus 3y equals 1. Tell me how to solve that for y. Then what? Divide by 3. All right, so far so good. Bottom one says 4x plus y equals negative 3. How do we get y by itself now? Subtract 4x. All right, so now we're comparing is the slope the same? The y-intercept the same? So it's not going to be infinitely many solutions. It's not going to be no solutions. We're going to get an answer from this. That's what we like. That is consistent. And it is independent. We're going to get one answer. And that's exactly what we like in that. Because then it's checkable too. You know, you can just put the numbers back in and make sure they're good one. All right, let's look at C over here. Cool, they already did some work for us. That one's ready to go. What do you want to do with the 6x minus 3y equals 9? Subtract 6x. Then what? Divide by negative 3. So that's going to give us 2x minus 3. What does that mean? Infinitely many solutions. Exactly. It's the same line. So infinitely many solutions. Were we able to give a solution? Yeah. So is that consistent with what we like in math or inconsistent? It's consistent. We like that. We like to give an answer. Independent, one answer, or dependent, lots of answers? Dependent, lots of answers. So like I said, I think now if you go back and look at some of those problems, because we've just gone through this a little more thoroughly today, this is going to make a lot more sense when you look at 3-1. So take the extra time you need over the weekend for some of those problems. And, oops, I had better not get rid of this. But now we get to the heart of this particular chapter, and that is, we'd rather not do this graphically because unless you've got the graphing calculator, you can do the linear regression perfectly. And even then, our graphing calculator, it does some rounding. It can't help it. You know, it gets to 10 digits and it rounds. We're still not going to have a perfect answer. So our hope is always that we can find an answer algebraically and we can give perfect answers. Perfect answers in math are called elegant. We like to have the best answers possible in the best form possible. So we're going to solve linear systems algebraically today. You'll like this because you've done this before. It's just a matter of pulling it out of your memory here. So to solve linear systems algebraically, this says what whole dollar amount of one-day sales would make it more worthwhile to work at store B, and justify your reasoning. So what we have here is an intro problem to show us a situation where we might be using something like this. It says store A pays $35 per day plus a 10% commission on all sales. And store B, $10 per day plus 18% commission on sales. So you can draw graphs of income from each store, but the dollar amounts might be kind of difficult to read. So what we would want to do is figure out how can we represent these algebraically. I might use that as a start on Monday to pull us all back in to what we need. So let's go ahead and get to this in our first method that we're going to talk about in 3-2, which is going to be substitution. So problem 1, we're going to solve by substitution. There are two methods that we typically teach of solving systems by hand, and that's going to be substitution and elimination. So it says, what's the solution of this system of equations? 3x plus 4y equals 12, and 2x plus y equals 10. Now in the end, we're not going to tell you all the time which one you need to use. So if I look at this one, the way that I know I would like to use substitution for this is because of this right here. Whenever you see a variable that's either by itself or has a negative in front of it, that makes this problem a really good candidate for substitution. Because I realize that to get y all by itself, all I have to do is subtract 2x from both sides. And it will be y equals negative 2x plus 10. And why is that so great? Because what this means is whenever we see a y in the top equation, which we haven't done anything with, we can go ahead and put negative 2x plus 10 in there instead. So step one is all about solving one of the equations for one of the variables. Now pretty obviously we're good at this anyway. We could do it if it comes out to be, nasty fractions and things like that. But linear, I was going to call it the other name that they used in the old books. Elimination might do that a little easier. So what we want to do is use substitution when we know it's a good fit. So right now we have y equals negative 2x plus 10. We solved one of the equations for one of the variables. It's called substitution because that's exactly what we're going to do next. We're going to substitute that second equation, which we just rewrote, back into the first equation, because if we want to know where these intersect, we have to use them both at once. And so far, we've only touched one of them. So my top equation is 3x plus 4y equals 12. And what we're saying is y equals this. So instead of leaving y in this equation, we're going to go ahead and put in negative 2x plus 10. Look at that, and a really good thing just happened, because now this equation only has one variable. We absolutely are going to be able to figure out what x is, because we have just one variable at this point. So we'll go ahead and distribute, combine like terms, and solve. And don't forget to take the 4 times the 10 as well, to multiply that all the way through. And this will say negative 5x plus 40 equals 12. We'll subtract 40 from both sides. And then divide by that little negative 5. So we now have an exact answer for our x. We're not done yet. Because remember, visually what we're trying to do is we're trying to figure out where these two intersect each other. And it's not just the x that we want to be concerned with. We also want to figure out where the y is. So we substituted once, but that's not enough. We now need to take our x value, which we know. It's 28/5. And we're going to put it back into either one of our first two equations. It doesn't make any difference. And figure out what y is. So here's the deal. I'm going to go back. And obviously I'd like to find the easiest place to get the math that I need. So I look around. And I say to myself, well, these two are nice. I mean, they're not awful. But I built this equation, so it'll give me y. I mean, I built that equation for that purpose. Y equals this. So why not use this one? So really what I'm doing taking that 28 fifths and putting it back into my y equals negative 2x plus 10. Now, here's the what if. Let's just say we did this wrong. Now, all of this is wrong, and we're going to put a wrong answer back in here. Well, we can always check these. We can always put it back in the end and make sure they work. So that would be the best, easiest place to get our answer. So we'll have y equals negative 56 fifths, because with fractions we're going to do top times top, bottom times bottom. And then we could certainly do this by hand if we want to, and make our 10 50/5. But you could also use your calculator and use your math number 1 fraction key to get that back. And now we're almost done, because I would definitely add a step 4 to this, because we need to realize what we just found. We had one line, we had another line, they hit in one spot. So we need to represent this as an ordered pair. So my step 4 would be right as an ordered pair. The only time we won't do that is if it's a word problem. So we just finished up. The ordered pair 28 fifths, negative 6 fifths. And like I said, it's checkable. You know, and we can grab the calculator and put these in and make sure they work. So, let me get this rolls up so big. It was 3x plus 4y equals 12. And 2x plus y equals 10. And if we haven't used the calculator yet, maybe it's time to just get some use out of this. So we have 3 times, parentheses, 28 fifths, plus 4 times negative 6 fifths. 12. It checks. So on a test, I might do this. GC, check. That one's good, but it has to work in both. So 2 times 28 fifths plus a negative 6 fifths is 10. GC, and all is good. We know it's working. We got one solution, an independent, consistent solution. We wrote it as an ordered pair, and we're ready to go. All right. I know my computer doesn't like it, but the graphing calculator is still turned on. I hope it's not going to have a cow. There we go. All right, so x plus 3y equals 5, negative 2x minus 4y equals negative 5. Good candidate for substitution or not? What makes it a pretty good candidate? Yeah, some people are worried, but it's not the y this time. It doesn't matter. It doesn't matter which variable it is. So with step 1, we'd say x plus 3y equals 5, and what would you do? Subtract 3y. Now keep track of the fact that we just used the top equation. So now what do we need to do? Yeah, substitute it in there. So we'll do negative 2. I'll put this again. Times negative 3y plus 5 minus 4y equals negative 5. Something good just happened when we did that. How many variables do we have in there now? 1. I know how to solve this stuff. So we distribute carefully. times negative 3y is 6y. Negative 2 times 5 is negative 10. Go ahead and combine some like terms over here. A little three-stepper. That's what we're doing. We add 10 to both sides. And divide by 2. So fraction answer, but not necessarily a really ugly one. That's not too bad. All right, so we have that. That was step 2. Step 3. What do we need to do? Do you want number 1, number 2, or number 3? Yeah, well, why not? It's built to find x. Let's do that. So x equals negative 3 times our little 5/2 plus 5. Just put that right in there. So we'll have x equals, remember it's like a negative 3 over 1, so negative 15/2. What's 5 in halves? So what do we get? Creeps a little, make you feel like maybe that's not right. One positive, one negative. Well, let's put it all together. What's our ordered pair? Negative 5/2, 5/2. Yeah, it has to be x comma y. Negative 5/2, 5/2. All right. So let's go check these back in the original. Again, it's a matter of just grabbing the calculator at this point and getting those. So the top equation was x plus 3y equals 5. And the bottom one was negative 2x minus 4y is supposed to come out to be negative 5. Go ahead and punch them in. Check it for us. Make sure everything's going to be good. Checking out. Gotta work in both. GC, check. There we are. So now, word problem. See here. This says a music store offers piano lessons at a discount for customers buying new pianos. The cost for lessons and a one-time fee for materials, including music books, CDs, software, etc., are shown in the advertisement. What is the cost of each lesson and a one-time fee for materials? So really, what are you going to have to pay is what they're asking us here when you get them. All right, so let's see. It says over here, 6 lessons will cost $300. $300 seems like a total. So if that's my total, that total was for the 6 lessons. But what's hidden in the cost with those 6 lessons? What did it say that's in there? Yeah, so we're going to have 6 times something for the lessons. So let's have the cost of a lesson be X, but then we have a fee in addition to that, which is going to be Y. So this will be 6 lessons plus the fee is $300. You see another total up there for 12 lessons. How do we write the right-hand side of that equation? Good candidate for substitution? And kind of a double candidate, right? So which one would you use? Red one or green one? Red one, solving for y, okay? Then what would you do? Substitute into my green one there. It's good. Don't even have to distribute this time. Let's see. 30. What does that mean? That's how much the lessons were. So we can stop right now since it's a word problem and write $30 per lesson. We still need the fee. Where's a good place to put our $30 back in there to get the fee? Top colors to me up here. Where is it? Where should we take that $30 to find the fee? Red one right here. Built for it. Y equals. Stuck in my equal sign. So how much is the one time? 120. So $120 one time fee. There it is. So again, we could check this. We've got our two equations up there. We could actually think of this as a word problem and say, okay, does it make sense if they do 12 of these lessons and they add the one-time fee that they're going to get $480? You know, just think about it that way. But it's not so bad writing word problems when we know where we're trying to go with it. So on the next page, we've got an online music company, and they offer 15 downloads for $19.75 and 40 downloads for $43.50. Each price includes the same one-time registration fee. So kind of like the one-time fee that we had at the music store there. What is the cost of each download and registration fee? Give me a total that you see. $19.75. How did they come to get that total? 15 downloads, so I can have X be my number of downloads. Anything else or just the 15 downloads? The fee. You see another total. $43.50. And how did they come to that $43.50? 40 downloads? Just the 40 downloads? The fee, yep. Which one do you want to solve for what? Red or blue? Red one? Smaller numbers? Yeah, usually a good way to go. This one we're probably going to use a calculator for anyway. We're talking decimals. So now what do we do with this new red one? Plug it in. Right there. Just cut to the chase. You guys can tell me what the cost per download or number of downloads is. Cost per download. How much? For one download? $43.50 minus $19.75 divided by 25. Oh, I don't think you divided both. Then what do you do to get the fee? Plug it in. You got a good one? Red one looking pretty good right here. Anybody get it? $5.50? One-time fee? And again, it's a word problem, so we're not going to write this as an ordered pair. We're going to say 95 cents per download. And $5.50 one-time fee. That is just not in cards, folks. So, just, especially if this is, you're feeling good at this point, I don't want to like quickly rush through another one. So, 43210, how do you feel on substitution right now? Okay, I'm not going to try and shove something else in today. I'll just change the assignment real quick. We will just look at substitution. Oh yeah, we're changing that. I'll just cross it. Let's do the substitution ones. So let's do 10 through 19. Substitution 21. And this review. That'll be better anyway. We're going to need more practice at the substitution piece there. So 10 through 19, 21, 67 to 71, and 75 to 80. And some of you will be relieved that you won't need your graphic calculator for anything more than just doing, you know, addition, subtraction, multiplication, and division on there. Eventually, if you use the calculators enough, we'll become really comfortable with all of that, and it won't be a big deal.
So it's all like 10 to 19?
Yes, yes, those are substitution. And is next week our short week already?
Yep.
Yes.
Okay.